Section 3.3 Differentiation Rules. As a motivation, we will look at this particular problem. If y is equal to mx plus b, find the derivative y prime. And by definition, y prime is equal to the limit of f of x plus h minus f of x, whole thing divided by h, and we take the limit as h approaches 0. So for this one, it'll be m, or the limit of m times x plus h plus b minus mx plus b, whole thing divided by h. And we can simplify terms here, because if we take now the limit of mx plus mh plus b minus mx minus whole thing will be divided by h. H approaches 0. This cancels out, and we are left with the limit of mh over h, and of course that's equal to m. That should be the derivative of the function where we have a line, because for any line y equal to mx plus b, the slope of the line tangent would be the line itself, so the slope will be m. So for all the following, we can just get y prime here to be equal to 3. For the second one, y prime will be negative 2. And here's just a diagonal line, so y prime would be 1. Now what about number 4? In number 4, we have a vertical, or rather a horizontal line passing through 2 for number 4, and the slope of this line is 0. So that means y prime is equal to 0. And if we can generalize, we can say that if we have a horizontal line, then the derivative of the function, a constant function, is equal to 0, because the slope of this horizontal line is 0. So the first rule of differentiation is that if f of x is a constant function, then the derivative of f with respect to x is 0. So if y is equal to 4, then y prime is 0. If y is equal to negative 5, y prime is still 0, and so on and so forth. Okay. Now let's see if we can find a pattern in finding derivatives. We've seen from the previous slide that the slope of this line is 1, and from the videos and the other discussions we had in class, we have found that y prime here, when y is equal to x squared, is equal to 2x. What about for y equal to x cubed? If we take the limit of x plus h cubed minus x cubed, whole thing divided by h, that is the definition of y prime. So if we expand this, so this is finding the derivative, so y prime is equal to this limit. And if we expand this, we're taking the limit of x cubed plus 3x squared h plus 3h squared x plus h cubed minus x cubed. Whole thing is divided by h, and we let h approach 0. And there are a few things that gets cancelled here, and we keep going. We take the limit, and notice that for the 3 terms that are left, we can pull out the h, and what's left inside is 3x squared plus 3xh plus h squared, whole thing divided by h. So that gets cancelled. We take the limit as h approaches 0. This all go to 0. This goes to 0. So the limit is equal to 3x squared. And if we do the same thing in number 4, there is a pattern, and if we expand the same way as we did here, we will discover that y prime is equal to 4x cubed. So there is some kind of pattern involved here, so that if y is equal to x to the n, y prime will be bring down the power of n multiplied by x raised to the n minus 1. So in this case, x is equal to x to the first power. So you bring down the power 1 times x to the 0, and that's why x to the 0 is 1. So it's still consistent with a linear function. If you have a quadratic, the derivative is 2x. If y is equal to x squared, y prime is equal to 2x. So bring down the power 2. X to the 2 minus 1 gives you x. So it's 2 times x, and so on and so forth. That's why if y is equal to x cubed, then the derivative is 3 times x squared. So if y is equal to x to the 4th, the derivative y prime would be 4 times x cubed. So if I have a general rule, I would say that the power rule for positive integers is that if y is equal to x to the n, then the derivative of x to the n is just n times x to the n minus 1. Again, for more examples, okay, if y is equal to x to the 6th, then we know that y prime is equal to 6x to the 5th. And if, say, y is equal to x to the 8th power, y prime would be 8x to the 7th. In fact, if n is equal to any, or if n is any real number, then the derivative of x to the n, the power rule still holds, okay, as long as x to the n and x to the n minus 1 are defined. So let's say we have y is equal to the square root of x, and we know that if I rewrite y equal to the square root of x, we can write it in exponential form as y is equal to x to the 1/2. If I take the derivative by the power rule, you bring down the power 1/2 times x to the 1/2 minus 1. So that's equal to 1/2 times x to the negative 1/2, which is equal to 1 over 2 times the square root of x. So if we've got another function, say y is equal to x to the 2/3. By definition of the power rule, y prime will be 2/3 times x raised to the 2/3 minus 1, which is equal to 2/3 times x to the negative 1/3. So if I rewrite that, it'll be 2 over 3x to the 1/3, or 2 over 3 cube root of x. Derivative constant multiple rule. If u is a differentiable function of x and c is a constant, then the derivative of c times u is equal to c times the derivative of u with respect to x. What does that mean? Suppose my function is y is equal to x squared, and I defined another function, say g of x, which is equal to 7x squared. So g of x is a multiple of x squared, that is, g of x is defined as 7 times x squared. So by the derivative constant multiple rule, g prime of x is just 7 times the derivative of x squared, which is 2x. So this is equal to 14x. Another example, suppose y, okay, let me write it. Y is equal to, we can define it as, say, 6x to the 5th. That means by the derivative constant multiple rule, y prime is equal to 6 times the derivative of x to the 5th. So 5x to the 4th, which is equal to 30x to the 4th, and so on and so forth. Derivative sum rule. If I have two functions u and v, and they are both differentiable, then the derivative of their sum can be differentiated by taking the derivative of each of the functions. So the derivative of u plus v with respect to x is equal to the derivative of u plus the derivative of v. both with respect to x. Well, let me take a particular example. Say y is equal to 4x squared plus 6x minus 7. So this is a sum of a quadratic and a linear function. And if I apply the rule, the sum rule, y prime will just be the derivative of each term, the sum of the derivative of each term. So the derivative of 4x squared is equal to 8x plus the derivative of 6x is 6, and of course the derivative of negative 7 is 0. So y prime is equal to 8x plus 6. Another example, let's say g of x is equal to 1 over the square root of x plus 4x cubed minus 11. What is g prime of x? Well, we can rewrite this first as x to the negative 1/2. That's another way of writing 1 over square root of x in terms of its exponents plus 4x cubed minus 11. And applying the power rule and the sum rule, this would be negative 1/2 x to the minus 1/2 minus 1 plus 4 times 3 would be 12x squared, and the derivative of constant is 0. And so negative 1/2 minus 1 is negative 3/2, so this becomes negative 1/2 x to the negative 3/2 plus 12x squared, or furthermore, it'll be equal to 1 over 2 x to the 3/2 plus 12x squared. What about product rule? Let's look at the definition first. You have two functions that are differentiable. If we take the derivative of the product of u and v, it's equal to u times the derivative of v plus v times the derivative of u. Let's take, say, I have y is equal to the function f of x times g of x. By the product rule, y prime just says that I'll take f of x and multiply with the derivative of the other function plus f prime of x times g of x, the derivative of the first times the second. Notice that it doesn't matter which order I take the derivative of, because it's just a sum. So if I have y equal to, say, x squared times x cubed plus 1, I can apply the derivative rule here. If I take y prime, I'll say it's equal to the derivative of the first times the second plus the derivative of the second times the first, or vice versa, as long as you take a derivative one at a time. So suppose we take x squared and multiply by the derivative of the second function, which is 3x squared, plus, now we take the derivative of x squared, it's equal to 2x times the function, the second function, x cubed plus 1. And here we can still simplify this by expanding on it, and it'll be 3x to the 4th plus 2x to the 4th plus 2x. So it's equal to 5x to the 4th plus 2x. Let's take another example. Suppose y is equal to x plus 1 times x squared minus 4x. So you have the first function times the second function. Y prime is equal to, take the first function, multiply by the derivative of the second, 2x minus 4, plus, now take the derivative of the first, the derivative of x plus 1 is 1, times the second function, x squared minus 4x. And this can just be simplified once you expand x plus 1 times, or you multiply x plus 1 times 2x minus 4. And here, notice that 2 is a common factor, so I can pull that out and say 2 times x plus 1 times, what's left here would be x minus 2 plus x squared minus 4x. And this is equal to 2 times the quantity x squared minus x minus 2 plus x squared minus 4x. And that's just equal to 2x squared minus 2x minus 4 plus x squared minus 4x. And if we continue to simplify, the final answer should be 3x squared by combining like terms minus 6x minus 4. So that's a derivative by applying the product rule. Now let's look at the quotient rule. The derivative of u over v is equal to, let's see what is the quotient rule. It's equal to, first you take the derivative of the top times the function at the bottom minus, now this time you take the derivative of the one in the denominator, dv by dx, times the function in the numerator. Whole thing is divided by the square of the function in the denominator. Let me give you an example to illustrate. Let y be equal to, say, x plus 1 over x minus 2. So if I have this quotient, I will take the derivative now by using this quotient rule. First of all, why don't we go ahead and square the denominator, because that's the square of the bottom. X minus 2 whole thing squared. Now what is the top? The top says you take the bottom and multiply by the derivative of the one in the numerator, and the derivative of x plus 1 is just 1. Minus, now you take whatever is the numerator on the top, x plus 1, okay, times the derivative of the denominator, which is 1. So if we simplify all of this, we will get x minus 2 minus x minus 1 whole thing would be divided by x minus 2 squared, and that gets further simplified into negative 3 all over x minus 2 squared. Let's take another example. Let's say y is equal to 2x divided by 3x squared plus 1. What would be y prime? Y prime is equal to, let's go ahead and square what's at the bottom, 3x squared plus 1, whole thing squared. Now what lies on the top? What would be put on the top? It says it's, you take what the function that's at the denominator, so let's take 3x squared plus 1, multiply by the derivative of the one on the top. What's the derivative of 2x? It's 2. Minus, take the function that's on the top, multiplied by the derivative of the denominator, which is equal to 6x. And all we need to do now is just simplify. 3x squared plus 1. And this becomes 6x squared plus 2 minus 12x squared. So that comes down to negative 6x squared plus 2, and the whole thing is divided by the quantity 3x squared plus 1 squared. Okay? Second and higher order derivatives. If I have a function y, I can take the second derivative or the third derivative, and so on and so forth. So let's say y is equal to 6x cubed plus 4x squared minus 3x plus 1. If I take the first derivative, it's equal to 18x squared plus 8x minus 3. To get the second derivative, I just take the derivative of the first derivative. So y double prime is equal to 36x plus 8. And if I continue, I can take the third derivative. It'll be 36. And furthermore, if I will take the fourth derivative, it'll be equal to 0. So this just shows that we can find higher order derivatives of a given function if they exist.